Hello everybody, I'm Prashant Mukhopadhyay, faculty member, Electrical Engineering Department, Greater Kolkata College of Engineering and Management. So in our last class of power electronics and drives, so we have discussed the say monostable multivibrator circuit and its application using IC 555 timer. And also we have started the monostable multivibrator circuit using IC 555 timer, and we have discussed the circuits of monostable multivibrator using IC 555 timer. So today we'll have a quick recapitulation of the last class, particularly the last portions of say monostable multivibrator using 555 IC. Its circuits actually it's a monostable means it has only one stable state. So in this circuit actually two extra components were used with IC 555 to make it work as a monostable multivibrator, that is resistor and a capacitor. So here it is shown resistor and capacitor. So as I told you in our earlier discussions also, and today at the very beginning, that monostable multivibrator has only one stable state. When a trigger input is applied, a pulse is produced at the output and returns back to the stable state after a time interval. The duration of time for which the pulse is high will depend on timing circuit that comprises a resistor and a capacitors. Details of the connections are given here. The pins 1 and 8 are connected to ground and supply VCC respectively. Output is taken at pin 3. And to avoid accidental reset of the circuit, pin 4 is connected to VCC. Pin 5, which is the control voltage input, should be grounded when not in use. To filter the noise, it is connected to ground via a small capacitor of capacitance 0.01 microfarad. So that is shown actually here. It is what I have told, that is discussed and that is shown in this circuit diagram. Now operation actually monostable mode is also called one-shot pulse generator. The sequence of events starts when a negative going trigger pulse is applied to trigger comparator. When this trigger comparator senses the short negative going trigger pulse to be just below the reference voltage, that is 1/3 of the VCC, the device triggers and the output goes high. Once again I am repeating, the sequence of events starts when a negative going trigger pulse is applied to the trigger comparator. When this trigger comparator senses the short negative going trigger pulse to be just below the reference voltage, that is 1/3 of the VCC, the device triggers and output goes high. The discharge transistor is turned off and the capacitor C, that is externally connected to its collector, will start charging to the maximum value through the resistor R. The high output pulse ends when the charge on the capacitor reaches 2/3 of the VCC. The internal connection of the ICC 555 in monostable mode along with RC timing circuit is shown here. So this is the circuit. Okay. The detailed operation can be stated like this. Initially the flip-flop is reset. This will allow the discharge transistors to go to saturation, and the capacitor C, this one, which is connected to the open collector say that is drain in this in the case of a CMOS, or here it is transistors, is provided with a discharge part, or this is the discharge part. Okay, hence the capacitor discharges completely and the voltage across it is 0 if when it is discharges to this path to transistors, saturation transistors. So its voltage will across it will be 0. The output at pin 3 will be low. Actually, here this is output, this will be low, that is 0. When a negative going trigger pulse input, this is the negative going trigger pulse input is applied to the trigger comparator, this one, this is the trigger comparator, comparator 2. So it is compared with a reference voltage of 1/3 sub voltage, reference voltage of 1/3 voltage. So this one, this is the comparator, this is negative going pulse applied to the comparator, inverting terminal, and this is the reference voltage 1/3 of VCC. Okay, so it is compared with the reference voltage of 1/3 VCC. The output remains low until the trigger input is greater than the reference voltage. The moment trigger voltage goes below 1/3 VCC, the output of the comparator goes high, and this will set the flip-flop. Here, this is the output, so this will set the flip-flop. So, and hence the output at pin 3 will become high. Yeah, this output will be high. Okay. And at the same time, the discharge transistor is turned off and the capacitor C will begin to charge, and the voltage across it rises exponentially. So this will actually this will be charged through this path. Okay, this is the charging path. So and at the it will be at the same time the discharge transistor is turned up and the capacitor C will begin to charge, and the voltage across it rises exponentially. And this is nothing but the threshold voltage at pin 6. Here it is. This is the threshold voltage at pin 6. Here. Okay. Now. This is given to the comparator 1 along with a reference voltage of 2/3 VCC. This is given to this threshold voltage to this comparator C, and this is the threshold voltage comparator with like this 2/3 of VCC. The output pin 3 will remain high until voltage across the capacitor reaches 2/3 of VCC, and the instant at which the threshold voltage, which is nothing but the voltage across the capacitor, becomes more than the reference voltage, the output comparator 1 goes high. This one, output the comparator goes high, and it will this will reset the flip-flop, and hence the output at pin 3 will fall to low, that is logic 0, and that is the output returns to its stable state. And as the output is low, the discharge transistor is driven to saturation, and the capacitor will completely discharge. So hence it can be noted that the output pin 3 is low at start. When the trigger becomes less than 1/3 of VCC, the output at pin 3 goes high, and when the threshold voltage is greater than 2/3 of VCC, the output becomes low until the occurrence of the next trigger pulse. Rectangular pulse is produced at the output, and the time for which the output stays high or the width of the rectangular pulse is controlled by the timing circuit, that is the charging time of the capacitor, which depends on the time constant RC of this RC network, which are the two extra component say connected to the triple five IC timer to work it as a monostable multivibrator. Now, how we can get the pulse width? So, as we know, the voltage across the capacitor rises exponentially. Hence, the equation for the capacitor voltage VC can be written as VC equal to VCC into 1 minus e to the power t by RC. When the capacitor voltage is 2/3 of VCC, so then it will be like this: VCC into 1 minus e to the power minus t by RC. And so if VCC is cancelled out from the both sides, so it will be 1 minus e to the power minus t by RC should be equal to 2/3. So e to the power minus t by RC will be 1/3, and say so t will be coming to 1.098 RC. And it's approximately you can write it 1.1 RC. So pulse width of the output rectangular pulse is equal to 1.1 of RC. So waveforms of the monostable operation is shown here. This is trigger pulse. This is the width of 1/3 VCC. This is the capacitor voltage, which is exponentially rising up to that is threshold voltage at 0.6. 2/3 of VCC, and this is the pulse width. So this is actually output voltage. So this is pulse width. Now, so that's all about your say the operation of IC 555 timer as say monostable multivibrator. So this is very important. Negative going pulse when it is reaches to this 1/3 voltage with the comparator 1. So output of the the flip flop will be, it is set and it will be at high. So again, this is 2/3. This is the threshold. This is exponential rising of the capacitor voltage, and this is pulse width of the say output voltage. So all this thing, and you know, also from this RC is the deciding factor to find out the pulse rate here. That is T equal to 1.1 RC mostly. Once again, I am telling this is the circuit. Okay, this is the schematic of say monostable multivibrator using 555 timer, and this is waveform actually. This is the waveform. Okay, this is turned on here. So now we'll discuss about the application of monostable multivibrator as a frequency divider. When IC 555 is used as a monostable multivibrator, a positive going rectangular pulse is available at the output when a negative going pulse of the short duration is applied to the trigger input. That is very important because when IC 555 is used as a monostable multivibrator, a positive going rectangular pulse is available at the output, that is at the pin number 3, and that is when a negative going pulse of short duration is applied at the trigger input. So now by adjusting the time interval T of the charging or timing circuit, the device can be made to work as a frequency divider circuit. Okay, and if the timing interval T is made slightly larger than the time period of the input pulse, that is trigger pulse, the device can act as a divide by 2 circuit. The timing interval can be controlled by appropriately choosing the values of the resistor R and the capacitor C in the timing circuit, because you know the T is actually 1.1 into RC. The waveforms of the input and output signal corresponding to divide by 2 circuits are shown here. it is okay. See, so this is once again I am repeating applications of monostable multivibrator as a frequency divider. So when IC 555 timer circuit is used as a monostable multivibrator, a positive going rectangular pulse is available at the output, when a negative going pulse of short duration is applied at the trigger input. By adjusting the time interval T of the charging or timing circuit, the device can be made to work as a frequency divider circuit. Now, if timing interval T is made slightly larger than the time period of the input pulse, that is trigger pulse, the device can act as a divide by 2 circuit. The timing interval can be controlled by appropriately choosing the values of resistor R and capacitor C in the timing circuit. As you know, RC is the time constant of the timing circuit, and the waveforms of the input and the output signal corresponding to divide by 2 circuits are like this. So this is the trigger, this is the output. Okay, this is output changes, this is no changes, again output changes here. So the circuit will trigger for the first negative pulse of the trigger input, and as a result the output will go to high state, and the output will remain high for the time interval T. It will remain high, and during this interval, even if a second negative going trigger pulse is applied, the output will not be affected, since it is a monostable one, not be affected and continues to remain high as the timing interval is greater than the period of the trigger pulse. On the third negative going trigger pulse, the circuit is re-triggered. See, this is the third negative going say trigger pulse. So the circuit will trigger on every alternate negative going trigger pulse, and there is one output pulse for every 2 input pulse. See, this is one output pulse. So hence it is a divide by 2 circuit by adjusting the timing interval. So the monostable circuit can be made to produce integral fractions of the input frequency. So in this way, a monostable multivibrator circuit using 555 timer can be used as a frequency divider circuit. Okay, now we'll discuss another example of monostable multivibrator using 555 timer, that is pulse width modulation. Say monostable made up operation of the IC 555 can be turned into a pulse width modulator by applying a modulating signal as the control voltage at the pin 5, and the circuit for a pulse width modulator using a monostable multivibrator is shown here. Okay, this is the control signal applied at the pin 5. This is the negative trigger pulse applied 2, and this is 3, the output pulse. So this is output pulse. Okay, so actually the control signal will modulate the threshold voltage, and as a result threshold voltage is applied at pin 6. And as a result the output pulse width is modulated. See, this is the output pulse width is modulated. At the control voltage, there is the threshold voltage, which is the input to the comparator 1, also varies. And as a result, the time for charging the capacitor to the threshold volt level will vary, and resulting in say a pulse with a modulated wave at the output. The waveform of the input, output, and the modulated signal is shown as we told you. This is the input trigger pulse. This is modulated signal, and see this is the pulse with modulated output. So see, it is modulated. It is changing with this modulating signal. Okay. So due to the application of the control signal that is applied at the pin 5, the upper threshold voltage level of the capacitor will be different, and the new upper threshold voltage threshold level UTL is given by 2/3 of VCC plus this modulating voltage B mod. So it is the voltage of the modulating signal. So because of the new threshold level, the pulse width of the output is given by, so this is equal to minus RC ln 1 minus UTL by VCC. So the time period of the output is the same as the input. See, time period is same, but your see pulse width is being modulated. It is changed. Okay. So that's way by applying a modulating signal, which is work as a control signal at which is applied at the pin 5. The output pulse can be modulated due to the presence of the say this control signal, that is the modulated voltage. The upper threshold level will be changed, and new upper threshold level will be like this, 2/3 VCC plus remote, and as a result, this application of this level new, because of this new threshold level, the pulse width of the output is given by this minus RC, and then so this U12 minus U12 by VCC, and as a result, the time period of the output, though it is same as the input, so pulse width will be changed. So this is another example of monostable multivibrator using 555 IC timer IC. So now we'll discuss another applications of monostable multivibrator using IC 555 timer circuit. So this is linear ramp generator. Okay. The monostable multivibrator will act as a linear ramp generator with the addition of constant current source. So you have to apply a constant current source, and a current meter consisting of a diode and a PNP transistor is used as a constant current source. This constant current source is consists of a diode and a PNP transistor. This constant current source is positioned in place of the timing resistors here. So the circuit for a linear ramp generator using 555 IC timer circuit in monostable mode is shown here. So this is like this. This is ramp output. Let us see constant a current IC from the constant current source. This is the current IC. The constant current source will charge the capacitors. This will charge this capacitor at a constant rate towards the peak voltage VCC, resulting in a rising linear RAM. As the voltage across the capacitor reaches 2/3 of VCC, the comparator 1 will drive the discharge transistor to the saturation. As a result, the capacitor starts discharging, and while discharging, as the voltage across the capacitor falls to 1/3 of VCC, the comparator 2 will turn off the discharge capacitor. Hence, the capacitor will start charging again, and the discharge time of the capacitor is very less when compared to the charging time. And as a result, the downward ramp is very stiff, almost an immediate discharge. Hence, the time period of the ramp output is practically equal to the charging time of the capacitor. And the time period of the RAM output is approximately given as like this: T equal to 2/3 of VCC RE into R1 plus R2 into C whole divided by R1 VCC minus VB R1 plus R2. So this is the actually approximate time period of the ramp output. And the waveform of the ramp output and the pulse output of a ramp generator is shown here. So this is the pin 3 output and this is output at pin 6. This is ramp output. Okay, so this is varying from 1/3 to 2/3 of the supply voltage. This is time period. So that is actually a unique application of a monostable multivibrator using IC 555 timer circuit as a linear ramp generator. So once again, I'm repeating this discussion. It acts as a linear ramp generator with the addition of a constant current source which supplies this constant current IC for charging this capacitor. And this constant current source is consists of a diode and a PNP transistors, and it is positioned in place of the timing resistors. That is actually we are finding in a monostable multivibrator circuit using 555 timer. The circuit for a linear ramp generator with IC 555 is shown in monostable mode. Okay, the constant current IC from the constant current source will charge the capacitor at the constant rate towards the peak voltage VCC, resulting in a rising linear ramp. And as the voltage across the capacitor reaches 2/3 of VCC, the comparator 1 will drive the discharge transistor to saturation, and as a result, the capacitor starts discharging. While discharging, as the voltage across the capacitor falls to 1/3 of VCC, the comparator 2 will turn off the discharge capacitor, and as the capacitor will start charging again, and discharge timing of the capacitor is very less when compared to the charging time, and as a result the downward ramp is very steep, almost an immediate discharge. Hence the period of the ramp output is practically equal to the charging time of the capacitor, and the time period of the ramp output is approximately given by this equation. And the waveform of the ramp output and the pulse output of a ramp generator are given here. So this is the waveform, the output pin at 3. Okay, output at pin 3, and this is at output at pin 6. So that is steeply rising from 1/3 of VCC to 2/3 of VCC, and then it's like a ramp generator. So that's all of monostable multivibrator using 555 timer circuit to use as a linear ramp generators. So far we have discussed the application of monostable multivibrator as a frequency divider circuit, as a pulse width modulator circuit, then we linear ramp generator circuit.